All right, so we're going to continue our diffeqs or differentiation, anti-differentiation, and introduce the idea of integration. The example that we did in the last video, example 3, this is called a separable differential equation because you can get the x's and the y variables on either side. Okay, so when you're given a differential equation in Leibniz form, and remember that's like our dy dx, it is mandatory to show the separation of variables, okay, by writing it in differential form. And that looks like this. That's where we just throw the dx on the other side. So dy equals, like, whatever the function is, dx. And we'll talk about why that's important in a little while. So what we're going to be doing to go backwards here, what we're going to do, and it's kind of explained in the bottom. So we have this here. We have, I'll just write it, dy equals f of x dx. The only new thing we're going to do is write this little symbol. All right, that is called an integral. So we're finally on that second half of our house of calculus. We built the foundation. You're great with limits. We built some of it because we have a nice part of derivatives and applications for that. And now we're finally getting to that other part. And so the antiderivative, okay, or if we integrate dy, we would just get y equals. We integrate this, we get that capital F, the antiderivative, plus some constant. All right, so this is our basic indefinite integral, and it's not definite because we're just looking at certain values, like general cases. All right, we'll talk about definite ones later, but for right now, we're just we're taking the antiderivative. So this is the integral symbol here. This, whatever's inside here, is called the integrand, and whatever's out here is the variable of integration. And we'll get to practice these in our next couple of examples. All right, so notice this one, example 4 says find the particular solution to the following diffeq, okay, differential equation, if dy dx equals this. We have this function and we have this piece of information here. So whenever we have it in this notation, the Leibniz notation, the first thing we need to do is rewrite it so we're separating the variables. Okay, e to the x. Now, I don't know if I like it written that way with that negative exponent because I don't know how to undo a chain rule yet or anything like that. So I'm going to maybe write it, instead of writing it like 20 over this or 20 times this to the negative first, I'm just going to write it like that. Okay, I like that better. It just looks better to me. All right, so we have this piece, and then I'm going to separate it. All the x's are on that side, so I'm going to write dx. Now our new idea, we integrate both sides. Okay, the antiderivative, or if you integrate dy, you just get y plus a constant, right? I'll call it plus c1 equals, integrate e to the x, that's just e to the x. All right, now, do you recognize this? Hopefully you do. It'll make me very happy. The antiderivative of that is arctan, or inverse tangent. And now that dx is there to remind us to put plus c. And I'm going to put plus c2. Just because that's another constant. It's not the same. Now, one thing that we're going to do, you'll never have to do this c1, c2 thing again. All right? If I move that to the other side, that's c1. So I'll get c2 minus c1. But this right here is just a constant. Okay, so from this point on, you don't have to do the plus c on both sides as long as you remember it on one side. So don't worry about the dy side, okay? Just worry about one side because it's just a constant value. It doesn't matter if you have a part of the constant on one side, part of the constant on the other. All right? This is our general equation. Now, this isn't what we were looking for. Okay, now we have to use that information. So negative 2 equals e to the 0 is just 1. Okay, arctan of 0 would be 0. So that part we don't need, plus c. So it looks like our c value is -3. So our particular solution, our very specific one of that family of antiderivatives, our particular solution is going to be y equals e to the x plus 20 inverse tan or arctan of x. Whoa. Okay, minus 3. There we go. That is our particular solution. So we have this is a good example of a problem you might see on a free response. The separable differential equations. If you just separate the variables, you could get a point right there usually. Sometimes you even get a point just for remembering to put the constant value there. Okay, and I'll talk more about that as we go on. Let's try another one here. Now this time, because it is in this notation, you're not going to be required to do that separating the variables, okay, because you're not quite ready for that. This is called a second order differential equation, or second order diff EQ, because it's a second derivative. So you're only worried about separating the variables like we did right here when you have dy dx. You don't have to worry about any other higher. It's only for first order derivatives. All right, but we have that first derivative, so we could take the antiderivative of that. Dy dx equals, now we have, what do I have here? 12x squared, add 1 to the power, divide by that new power. You get 4x cubed plus 3x squared minus 4x plus c. Now we have these points we could plug in. 3 equals 4 plus 3 minus 4 plus c. So it looks like c equals 0. Now we can go ahead and at this point, so dy equals 4x cubed plus 3x squared minus 4x, and no plus c because our c was 0. But I will write the dx on this side. Okay, new step, integrate. This is y, and remember we don't have to put the plus c because we're taking care of it on the other side. This time we'll get x to the 4th plus x cubed minus 2x squared plus c. We have another point. Let's plug it in. -6 equals c. Look, that was an easy one because all the other parts are 0. So our final equation, our particular solution to this problem is y equals x to the 4th plus x cubed minus 2x squared minus 6. All right, that is our particular solution. So again, talking about the AP exam, the free response section, usually, let's say if I'm starting at this point, our first order differential equation, you get a point just for separating the variables on almost every problem. All right, you get a point just for doing the antiderivative correctly. Sometimes you even get a point just for writing plus c. So if you can just remember that, that's a good step. You would get a point for using this value, and you get a point for plugging it in for your final answer. So you could get 5 different points here, just for taking little steps. All right, so let's move on to this next one because this one's a little bit different. I'm gonna just pick up where we left off here. Dy equals 4x cubed plus 3x squared. Minus 4x plus c dx. All right, so this one's going to be a little bit different because I don't have y prime of any number. I don't have any values that work for this. All right, so we're going to integrate again. Y equals x to the 4th plus x cubed, and again, we just did this, plus, this time, plus cx, some constant times x, plus, pick a different letter. I'm going to say maybe k. because that's still constant, same sound. All right, so let's plug in our points now. 4 equals, looks like everything cancels out but the k. All right, so then we have this equation, x to the 4th plus x cubed minus 2x squared plus cx plus 4. Okay, plug in the rest of your values. So 1 equals 1 plus 1 minus 2 plus c plus 4. So it looks like c is -3. So our function, our particular solution to this is y equals x to the 4th plus x cubed minus 2x squared minus 3x plus 4. Okay, and I plugged in that c and the k value. So look, we started with the same second order differential equation, but we ended up with 2 completely different answers. Okay, and that's okay. That's why we need to put that plus c and find these specific values. All right, so now there are 2 things left. So I'm going to leave one for you to do. I think maybe B is a little bit harder. So this is, if you remember, this is a little side work here. Tangent squared, let's say P, because I'm just using that. 1 plus that equals secant squared of P. And 1 plus cotangent squared of P equals cosecant squared of P. Now these are just our Pythagorean identities. This is something that you need to know. But you memorize everything we've ever learned, so it's fine. So anytime you see tangent squared or cotangent squared, you probably have to use these identities. So another way of writing this, instead of writing tangent squared P, I'm going to use this and write secant squared P minus 1. And I still have that plus 4 there, dp. So I can simplify this a little. Secant squared P plus 3 dp. Now, the reason why I did that, because I can't think of anything that when you take the derivative, you get tangent squared. But I do remember that if I take the derivative and get secant squared, that original function must have been tangent. Okay, and then we have a constant, so it'll just be 3p. And that dp is there to remind us to put plus c. So this is the antiderivative. Okay, if we integrate that function, this is what we end up with. So of course I saved the best one for last. I'd like you guys to simplify this, evaluate it, and put in this in your summary part of the WISC. So you have trig functions. Maybe you can manipulate those to get this value. All right, give it a little try. See you in class.